Okay, let's dive right into this. We're embarking on one of the absolute most mind-blowing scientific detective stories of the past century. Think about it. How did humanity actually manage to visually capture the physical atoms of a tiny 3 millimeter piece of metal? I mean, for you and me, zooming in on photos on our phones is totally second nature. But zooming in until you literally see the fundamental building blocks of the universe? No way. That was deemed entirely physically impossible just 30 years ago.
So the very first question we got to ask here is, why is it so hard to see atoms in the first place? Like, why couldn't we just take a regular piece of metal, stick it under a super powerful optical microscope, and just, keep zooming in infinitely using visible light? It sounds perfectly logical, right? Well, as you'll see, the laws of physics had a very different plan for us.
Which brings us to part one, the problem with light.
You see, we rely on visible light to see literally everything around us. Light travels in waves, and those waves have lengths between about 380 and 750 nanometers. But an atom? An atom is incredibly tiny. We're talking just zero point 0.1 nanometers across. Because the wavelength of visible light is so vastly larger than the atom you're trying to look at, the light just diffracts. It bends right around the atom. It's kind of like a massive ocean wave just rolling right past a tiny pebble in the water. Actually, scratch that, more like a grain of sand. The wave doesn't even notice it's there. And that leaves us completely blind to the nanoscale world. Just to put that into perspective for a second, an atom is over 3,000 times smaller than the absolute shortest wavelength of visible light. 3,000 times. That means optical microscopes don't just need like a slight technological upgrade, they hit a literal, unbreakable brick wall in physics. If you want to see an atom, you absolutely have to find something with a wavelength thousands of times smaller than light itself.
So let's look at part two, the electron solution.
How exactly do you see when light itself is too big? Well, you have to find a completely new way to see. Back in the 1920s, physicists found this brilliant workaround. A French physicist named Louis de Broglie figured out what is basically a physical cheat code for the universe. He discovered wave-particle duality, the idea that matter itself, not just light, has a wavelength. He proved you could calculate this wavelength by taking Planck's constant and dividing it by an object's momentum. So what does this actually mean for us? It means if we take electrons and we accelerate them to, say, 80% the speed of light, their massive momentum shrinks their wavelength down to roughly 2 to 3 picometers.
And the results of that math? It's absolutely staggering. By using high-speed electrons instead of visible light, scientists suddenly had access to wavelengths that were over 100,000 times smaller. 100,000. Theoretically, this unlocked 100,000 times more resolution. Just like that, the invisible world was suddenly within reach. But there's a catch. You can't exactly focus electrons with regular glass. So, in 1931, Ernst Ruska engineered a wild solution. He boiled electrons off a tungsten filament, accelerated them, and then ran them through this donut-shaped electromagnet. By using something called the Lorenz's force, the magnetic field pushes the electrons into a spiral, which gracefully steers the entire beam into a perfectly focused center. This ingenious invention birthed the very first transmission electron microscope, or TEM, and it was a total game changer, quickly surpassing regular optical microscopes to let scientists see things like viruses and bacteria for the very first time. But it wasn't smooth sailing for long. Welcome to part 3, the spherical aberration roadblock. Just as scientists thought they were on the verge of easily zooming right in on the atom, they hit another wall. As they cranked up the magnification on these new microscopes, the images became irreparably blurry. In 1936, a physicist named Otto Scherzer published a paper explaining exactly why this was happening. It's a phenomenon called spherical aberration. See, the magnetic field of the lens doesn't scale linearly. It's actually much stronger near the outer edges. So the electrons traveling near the edge of the lens get over-deflected and they focus way too early, while the electrons in the center focus later. Instead of giving you a sharp single focal point, the focus just smears out across the axis. It turns everything into a frustrating, blurry mess. Now, with normal glass lenses, like the ones in your camera or your glasses, you can fix this pretty easily by just adding a reverse, diverging lens to cancel out the blur. But Scherzer's theorem proved this is mathematically impossible to do with magnets. Because of Maxwell's equations, which govern magnetic closed loops, magnetic fields always converge an electron beam. They can never diverge it. Magnets just don't work that way. Physics literally dictated that a diverging, correcting lens could not exist.
And that brings us to part 4, decades of workarounds.
Scherzer's rigid mathematical proof completely stalled the quest for true atomic imaging. It plunged the whole field into this long, dark night of the soul. For over half a century, the TM was practically stuck. And people tried everything. In the 1950s, the field ion microscope managed to map the tips of needles by shooting gas at them, but it was incredibly limited. Even brilliant innovations like Albert Crew's ultra-bright scanning electron beam in 1970, which actually mapped single atoms, ultimately hit the exact same spherical aberration limit when researchers tried to really see the structural details of those atoms. The blur remained undefeated.
The scientific community was just incredibly frustrated. As physicist Albert Crew put it, they were forced to admit defeat after many heartbreaking attempts. I mean, imagine dedicating a decade of your life to solving a problem, only to have the laws of physics consistently shut the door in your face. After more than 10 years of fighting the complex mathematics of magnets, even the absolute most brilliant minds on the planet were forced to surrender to spherical aberration.
But of course, the story doesn't end there. Part 5, Breaking the Symmetry.
Science is fundamentally a process of perseverance, right? Enter our underdog heroes, a group of scientific troublemakers named Knut Urban, Max Heider, and Harold Rose. These three realized there was one massive hidden loophole in Scherzer's seemingly unbreakable theorem. Scherzer's absolute limit only applied to radially symmetric lenses. So their crazy idea, intentionally break that radial symmetry. Now, to everyone else in the field at the time, this was considered pure madness. Breaking the symmetry of a lens is supposed to instantly and completely destroy the image. But they really believed, that if they abandoned symmetry entirely, they just might find a way through the barrier. This brings us to what I think is one of the most elegant engineering solutions in modern physics, the hexapole solution. They used massive, bumpy electromagnets called hexapoles to deliberately distort the electron beam. They essentially twisted the flat 2D image into this bizarre triangular saddle shape. By doing this, they managed to squeeze out a tiny bit of central beam divergence. Then, they meticulously forced the beam through a second hexapole to unbend the distortion. If their mouth was absolutely perfect, that tiny engineered divergence would perfectly cancel out the original spherical aberration.
Which leads us to Part 6, Finally Seeing the Invisible.
So, did this wild theory actually work? Against all odds? It did. In July 1997, just one single week before their funding was set to dry up completely, the team turned on their highly unstable machine in the dead of night, let those massive magnets settle down, and achieved the impossible. By breaking the rules of symmetry, they slashed the resolution down to a jaw-dropping 0.13 nanometers. In an instant, those frustrating blurry blobs that had haunted scientists for 60 whole years transformed into crystal-clear, beautiful images of individual atoms. They had actually done it. So why does this matter to you and me today? Well, this isn't just some neat visual trick to print on a science poster. Correcting aberrations is an absolute necessity for modern materials engineering. It allows us to precisely measure atomic distances, identify specific atoms, and relate a material's physical properties directly to its structure. If you're out there developing new batteries, or stronger aerospace alloys, or next-generation microchips, and you can't see the structure at the atomic level, you literally only have half the information. This breakthrough was, without a doubt, the ultimate game changer. It leaves us with a pretty thrilling question. Now that these renegade scientists have given us the power to clearly see and precisely measure the invisible building blocks of reality, what incredible futuristic materials are we going to engineer next? We've unlocked the ultimate map of matter. Now it's really just a question of what we decide to build with it. Thanks for joining me on this explainer, and remember to keep your curiosity sharp.